Hello, everyone. My name is Leno, and this is joint work with Ruben Glatt, also from the Lawrence Livermore National Lab, Rafael Colby from Advanced Institute for AI, and Renato Vicente from Serasa Experian in Brazil. So, most of you already know that gathering data and building new data sets is a very costly and very difficult problem. But we can alleviate some of the costs and some of the risks of building new data sets by reusing knowledge. The main idea is that we could get knowledge or samples from a different task that is similar, and then we can reuse them to learn faster or using fewer samples. But this is not a very easy thing to do, because in many situations we have a situation like the one explaining the slide. So basically we have a source task in which we have data for, and we have the observations and the labels, and we then are able to train a classifier that, given the observation, the classifier is able to predict what is the correct label. But for the target task, we might only have the observations and no ground truthing labels at all. So how could we train a classifier in this situation? And this is not a very easy thing to do directly from using the data from the source task, because even though they are similar, we might have a situation in which we have covariate drift, which means that the samples are sampled in a different way, or the concept drift that, given the same observation, the label might be different from one test to another. So how can we address that? What is our proposal to address that? So our idea is to learn a mapping function that will translate data from the target task as if the data was from the source task. And then we have a simulation like the one shown in the slide, that by using the mapping function f, we translate the sample from the target task in a way that you can directly use a classifier from the source task and have the correct label predicted. An example of how this could work: let's assume that we have a model trained in data from Brazil. So we have the data from Brazil, we have trained the model, and we have the model for Brazil. But we want to apply this in Laos now. But the population in Brazil and Laos might be completely different or a little bit different. For that, we train a mapping function that learns how those two populations relate and how you can translate from one to another. In execution time, you will have a sample from Laos. The sample from Laos is translated to a virtual Brazilian sample that corresponds to the sample from Laos that you want to classify. And the source model from Brazil can be directly used to predict what is the label. For doing that, we leverage GAN models that are illustrated here in the slide. Basically, you have a discriminator in a generator model. The generator tries to generate samples that mimic the data from the real world, and the discriminator tries to distinguish which are the synthetic data and which are the real data. And the idea is that both the generator and the discriminator evolve over time until the generator is so good in generating new samples that the discriminator is not able anymore to tell apart the real data and the synthetic data. So for using GANs in our specific application for mapping the data, we had to propose a new GAN training cost function. And our cost function uses the regular discriminator cost function that the regular GAN already uses, the cycle cost that is also used by the regular cycle GAN, and then the new part of the cost function that predicts how much is the translating function precise in translating the data in a way that you will be able to translate the sample and still get the right label for that specific test. And for testing our model, we use the circle domain. The circle domain is illustrated in this slide. Basically, you have a circle and you have to classify if a given point is inside or outside the circle. And the circle might change in radius or in the way you sample the points that you want to classify. And we explore some different ways of doing that. In the end, our results are that if we use the source model directly, if we get, let's say, the model from Brazil and use it directly, the accuracy would be almost 50%, 49.3%. If we use the data from the target task directly, so in the real world, we shouldn't have this data, so this shouldn't be possible, but this is the highest possible accuracy that you could achieve in this task. And this highest possible accuracy is around 92% for this domain. But by using the mapping function through our modified GAN cost function, we were able to achieve 83%. So compared to the maximum baseline possible using information that we wouldn't have in the real world, we only decreased the 9% accuracy. And it's almost, it's more than 30% more efficient than using the source model directly. So the conclusion is that we proposed a novel data mapping method based on GANs for using transfer learning. And our preliminary experience show very promising results. So thank you. I hope you have the time to read the paper to learn more about the details of this work, or to talk to us during the poster section.